Hi there, welcome to lesson 2 of kinetic theory or particle model of matter. And today we're going to be looking at, my computer's being a bit funny. Today we're going to look at like energy transfers and how that compares to their internal transfers. So first of all, let's have a look at this. Here are some gas particles, and I'm going to let them do what gas particles do, which is move around freely, bumping into the sides of the container, moving very, very fast and free. Okay, so let you look at that again. So they're moving very, very freely, bouncing around off the container, not really constrained by anything, not holding on to each other, no forces of attraction between them. They're just doing what they want, a little bit like students. So if we turn up the temperature a little bit or add a little bit of energy, because remember temperature is just another word for measuring internal energy. If we give it some internal energy, then they move around faster. And when they move around faster, think about that. If they're moving around faster, there's more chance they'll bump into each other. There's more chance that they'll bump into the container. So they'll bump into the container more often. They'll also bump into each other with more force. They'll also bump into the container with more force. So in other words, when force is exerted over a surface area, then what we get is something else in physics, which is called an increasing pressure. So they're going to be forcing and pressurizing and providing a massive force against the outside of the container. So the notices that we need to make is what changes happen when it gets hotter. They move faster. And how does it affect the spacing? Well, they might appear to be closer, but they're not actually any closer because it's a random movement. If they are closer, then it's only for a second or two because they're moving past each other. It's random. So the spacings are random, just as random as they are when they're moving slowly. It doesn't really affect them in that way. Okay, so let's have that. Let's look on this one now. Which one of these boxes has got the most internal energy? So, which of those boxes has got the most internal energy? And explain your answer. So, a short sentence about that, please, in your box. Off you go. Please pause the video. Okay, so if you've written a little sentence about that, here's how my explanation would have gone. Something along the lines of, it's the bottom box in both instances. Because there's the same number of particles, there's the same volume of space for the particles to move around in. It's just that the particles in the bottom two boxes are moving faster. And for it to move faster, it must possess more kinetic energy. And if it's got more kinetic energy, it's inside a box, so that's internal energy. So consider these gas particles again. They're moving around. And these are the little statements, so I'd like you to get into your book, please. So we've got some words on the bottom to try and help you. If you please pause the video now while you get this in your book. So hopefully you've put the internal energy of a gas is the total amount of kinetic energy and potential energy of all the gas molecules added together. If a substance is heated up, its internal energy increases. This will either cause an increase in temperature or a change of state. So Take, for instance, this Bunsen burner and a beaker containing water. If we heat the beaker up, it's fairly clear that the liquid will gain internal energy and it'll get hotter, or its temperature will increase. What three things does the increase in temperature depend upon? Have a think about that for a second and pause the video. Well, firstly, the amount of liquid. So that's the mass of the liquid. The amount of energy going to the liquid, i.e. how hot or how good is that Bunsen and how long is it on for? And the substance itself that's being heated. Is it water? Is it cooking oil? Is it stone? It all depends. Okay, so let's go through that again. The substance itself, the amount of energy being supplied and how long it's being supplied for, and the substance being heated, the substance itself. So when it comes to specific heat capacity then, from those three pieces of information, we can actually glean what the equation is. Because if the rise of temperature depends upon the mass of the liquid and how much energy is given to the substance, how long it's being given for, and the substance itself, then we can say that the amount of energy required to raise something's temperature is its mass, M. This thing called specific heat capacity, which is specific heat capacity specific to the substance, so that's the substance itself, and the increase in temperature, so that's how much it gets heated by. Now, that might not jump out at you so clearly, but we've got the Bunsen burner, we've got the amount of water, and we've got how much it will raise it by. Okay, so you don't need to remember this equation. You're going to get it into your books from me now, though, please, while we're learning. But lastly, I need to give you what each of those things stands for so you can get it in there. So E is the amount of energy. Obviously, it's measured in joules because all energies are. Mass is in kilograms. Specific heat capacity is a joule per kilogram Celsius or Kelvin, depending on which scale you're working in. And delta theta is change in temperature, which is degrees Celsius. So if we pause our video and get that into our books now, again, I'll just remind you before you do, you don't need to remember it, but you need to use it. So if we pause the video and people get that in. And let's have a look at a definition. So this is the definition. The specific heat capacity can be thought of as the ability of an object to store its own energy or store energy. Its proper definition is, and this is what needs to go into your book, the amount of energy needed to raise the temperature of 1 kilogram of a substance by 1 degree. So if we pause our video while we get that in, because I just got a bit ahead of myself there. And if we carry on now. So here are some example questions. I've put that on the top there to help you. So 2 questions, pause the video now. These are probably 4 markers. Off you go. So here we go. We've got a beaker filled with 0.1 kilograms, that's a mass, with a specific heat capacity of, so that's a C, 4200. And we've got heated from 20 to 80. Now that's a change in temperature. It's not 80 and it's not 20, it's the change between them both, which is 60. So we've got 0.1 times 4,200 times by 60. If we calculate that, we should come up with that. We should come up with 25,200 joules. We got this other beaker containing 24 grams. Now 24 grams, you've got to convert that into kilograms. Okay, and that 24 grams is 24 thousandths of a kilogram, so it's 0.0024. Okay, we start at 50 degrees. If it loses 2000 joules of energy, what temperature has it dropped to? So we've got a rearrangement here. You probably struggled with this question quite a lot, and it's probably a little bit nasty of me or a little bit unfair of me, but you need to remember some things. And one of the key things to remember about this is water is one of our basic substances that we've got to know. And we should know that water specific heat capacity is around about 4,200 joules per kilogram Celsius. So all we got to do with this one is basically divide our energy by our mass that we've been given and this specific heat capacity, which we should know. Now, if you didn't know it, it doesn't matter. You can pause the video now and you can have a bash at it. But that should end up being 2000 divided by 0.024 times by 4,200. And it should give you an answer of around about 19.8, which when you take that away from 50, you end up with 30.20. So again, if you didn't get that, that is quite a stretching question because you're expected to remember some stuff. So some real life applications of specific heat capacity. So we've got these things here. Some people might have them there, especially they're used a lot in flats, really, not really in houses as such, but these are called storage heaters. And they were invented to utilize the fact that overnight electricity tariffs usually are a little bit cheaper. So what these night storage radiators did was, well, I'm not really going to tell you this time because I'd like you to have a go at trying to think about how it would work, why you should heat it up overnight. And there's also a question here, which is radiators can either be filled with inside these little rims here or ribs, can be filled with oil or they can be filled with water. Can you think of any advantages and disadvantages? I've given you underneath the specific heat capacity of water, which we've already talked about on the last slide. And I've also given you the specific heat capacity of an average oil. So have a think about those, talk amongst yourselves, and try and come up with an explanation for either of those two questions. And then we'll talk about them in a second. So please pause the video now. Okay, so night storage heaters, as I tried to explain to you before I nearly gave you the answer to the question. They utilize the fact that electricity is slightly cheaper overnight because nobody wants to use it because most people are in bed, unless you're a weirdo or you work nights. So they would fill up with energy overnight. And what would they fill up? Well, they would fill up these concrete blocks. And the material has a high specific heat capacity. So what does that do? Well, high specific heat capacity means that it takes a long time to warm it up. So energy is cheaper at night, so it can be left on running for longer and not cost as much. And these concrete blocks use the fact that they take a long time for them to really, really warm up. But if it takes something a long time to warm up, it also takes something a long time to cool down as well. So what they would do is heat up overnight, and then all the day after, they could be giving heat out again all day afterwards because it takes them so long to cool down. So when it takes something a long time to cool down, that means it can give out energy for a long time to the surroundings. Now, that's also leading into the next question, which radiators can either be filled with that. If you notice on the water has a much higher, roughly double the specific heat capacity of oil. So what's the advantages and disadvantages? Well, if you look at water, first of all, it takes a long time to warm up, but it also takes a long time to cool down. So there's an advantage and a disadvantage there in the fact that it takes a long time to warm up, so it will cost you a lot to warm it up, but it will keep warm for a long period of time. The oil's advantages and disadvantages are almost just the inverse of that. Oil has a low specific heat capacity, which means it warms up very, very quickly. But the disadvantage is it cools down very, very fast. So the uses of them, you could even go on and stretch yourself to say, well, specific heat capacity, the water-filled ones would be useful in a home where there's probably more activity from morning till night. Whereas oil-filled radiators would probably be very good for things like school classrooms or businesses where they can warm them up in the morning dead quickly. They can give out heat, but they don't need to heat the thing up overnight because in schools especially, you're not here overnight, are you? You've gone at 3 o'clock, so they can cool down and they're not wasting any energy. Okay. So let's have a look at this heating graph for ice. So we all know that ice forms below 0 degrees. So if we start taking some very, very cold ice at -50 and warming it up, then it's going to appear to do that. It's going to warm up from -50 to 0 degrees. Now, 0 degrees is the melting point, isn't it, for water? Now, something strange happens when we heat up ice. It doesn't change temperature for a period of time once it reaches 0. And then it begins to do what you would expect it to do in, say, for instance, a kettle. As we put some energy into it, it gets hotter and hotter and hotter over a period of time. But then when it reaches boiling point, you should have done experiments in the past when you was at primary school or in the early stages of secondary school where you kept a thermometer inside it, and you should have noticed that water doesn't really get any hotter when it's boiling. It stays at the same temperature. It stays at 100 degrees roughly. If it's slightly over or slightly under, that just shows you that there's some impurities in it. And obviously, after 100 degrees, once it's all gone, it's gas. It's in the room, then you can't be measuring it anymore. So notice that flat section there, because the reason it has that flat section is because this is what we call a change of state. It's going from a solid to a liquid, it's changing state. So all the energy that's going in there, instead of raising the temperature and increasing the energy, it's actually going in there to break the bonds between the solid structure and change it into a more fluid structure of a liquid. And there's a flat line at the top. That's where all the energy, again, instead of raising the temperature, is going into breaking the particle bonds and allowing them to float off or shoot off, as the case might be, into gas particles, not into changing the temperature. So you may have seen that before, you may not have seen that before, but now you need to understand that. So let's get that into our books, please. Save some space and write quite small as we sketch that into our book, because you can add other things to it from the next slide. Off you go. Please pause the video now. So hopefully you paused it, because what we can talk about now is the specific latent heat of a substance. That's the amount of energy it needs to change state from one thing to another. Okay, so the amount of energy it takes to change into something new is given by this equation. Energy equals mass times specific latent heat of fusion, or energy equals mass times specific latent heat of evaporation. And I'll show you the difference between them both, but basically they are the same equation. In GCSE, we tend to just worry about the fusion section, and I'll go through what fusion is in a little bit. So E is amount of energy, it's measured in joules. Mass is always measured in kilograms, and this specific latent heat thing is joules per kilogram. So how much energy goes in it per kilogram. So if we can get those into our books, please, as quickly as we can. Please pause the video now. So we can go back to our graph now and put a few more little labels on it, because this flat section here, where it didn't change temperature for a period of time, that is showing us where the latent heat of fusion occurs, because it's called fusion because, don't forget, you're going to see that this can go in two directions. You don't always have to go up in temperature, you can go down in temperature. And to go down in temperature, you would have to refuse all those bonds and turn it back into a solid to freeze it. Over here, this section here would give us, we would use the equation what I talked about of latent heat of vaporization, because we're finding out how much energy it is to re-engage or re-break all of the bonds, and how much energy it would take to put those bonds back together to turn it back into a liquid or condensate it. So, some example questions. There's a reminder of the equation, E equals ml. It's a very, very simple equation. Those 3 questions are all 2 markers. There's not much in there. The last one may go as far as saying 3 marks, maybe 4 marks top, because it's, you know, it's a little bit more difficult. But pause it, write those questions in, show me all your workings, and then we can go through it. Okay, so let's go through the answers here. So the latent heat of fusion for water is 334 kilojoules, per kilogram. So how much heat energy would be needed to melt 2 kilograms of ice? Now remember, it says kilojoules, so that is sorry for that strange pause. My AirPod fell out of my ear. So we was just on about kilojoules there, so that's 33 4 with 3 extra zeros on the end. So how much heat energy would be needed to melt 2 kilograms of ice? You don't need to really worry about the 3 extra zeros as long as you're answering kilojoules as well, because that's going to be, that's the L. 2 kilograms is the mass, so it's doubling it. Okay, now the next one, I'm presuming that you may have had some students saying, how can I do this? Well, how do I know whether all the ice or not? Well, you do, because your answer's up there. 334 kilojoules per kilogram. That's how much energy it takes to melt water. So this particular question said 0.5 kilograms of ice is supplied with 100 kilojoules of energy. Will all the ice melt? Well, let's go to our formula. We've got an amount of energy and we've got a mass. Okay, so if we divide our energy by our mass, we should get a number, and that number will probably be somewhere in the region of 100,000 divided by 0.5, which is 200,000. Now, will all the energy melt? Well, we've got an answer of 200,000. That's not the answer to the question. That's the answer to our workings. Now we've got to make the decision. Well, we've got 200,000. It takes over 300,000 kilojoules to melt ice. So we can make the assumption that it won't melt the ice because there's not enough heat energy. Okay. Another heater is used to boil off 100 grams of water. The latent heat of vaporization is a different number this time because this is vaporization. How much each energy was supplied to the water. So it's still the L. The vaporization is the L. And we've got 100 grams, so that's 0.1 of a kilogram. So how much heat would have to be supplied to get rid of that? So 0.1 times 2,260. Remember to keep the kilojoules on. And that should come back with 226 kilojoules. That's how much energy we'd have to use to boil 100 grams of water. Okay, thanks for listening. Any questions, email them.